So, my friends, I did just tell you that your final exam will not be cumulative. But there's a big but with that. Today we're going to do a bit of review of material that we learned in September. And so, while there isn't anything, there's not going to be any like, how many protons are in an atom type of questions on your final, all of chemistry builds on itself. And so I can tell you that yes, there won't be any Unit 1 questions like that on your final, but to say that it's not a cumulative exam is not really accurate, because if you don't remember how to balance chemical equations, you're cooked. If you don't remember how to write compounds and formulas, you're cooked as well. So those are just the sort of things that always we need to remember how to do. And so while it's not cumulative, I won't be asking electron configuration questions. Especially like stuff like today will be on the, it's just always important to remember that chemistry builds on itself. Okay, so we are still in the topic of equilibrium. And today we aren't going to be talking at all about the actual calculations of equilibrium, but what we're going to do is set up our knowledge and remember our learning so that we can be competent when things get pretty hard on Friday. I think that the most complicated material of the entire school year happens on this Friday, and so we're going to do our best to build up to that today so that we can be competent for Friday. Wednesday we'll do a lab. And it's a nice, beautiful, color-changing lab that everybody will like. Okay, today we're going to be talking about what's called the solubility product. The solubility product is an application of the concept of equilibrium. And we're not going to really talk about the equilibrium of it today, other than writing the K equation, but we've already been doing that. So what is the solubility product? Its abbreviation is KSP. K because it's an equilibrium constant, but SP because it's a special kind of equilibrium constant. SP stands for solubility product. So what does that mean? What is solubility? Solubility is the ability of a substance to dissolve in water. And so all of our solubility product chemical reactions will look the same. But we need to practice writing them because the amount of detail and correctness that you need to have is pretty up there. And any little error that you make, especially like at the very beginning when you're writing the formula of your compound, any little error will be propagated all throughout your entire work. And so we want to really be careful that we are attentive to detail. Okay, so what does a chemical reaction look like then for something that dissolves in water? This is what it will look like. So let's take a solid, let's take sodium chloride, and let's add it to water. If something does dissolve in water, what will happen is that its ions will break apart. And so we have to go back to this original compound and know what ions it will turn into. So that's why I asked you to take your periodic table out. So look on your periodic table and tell me what the charge of sodium is. +1. And then when it becomes an ion, it's in solution. So that means that we can't write solid anymore. We have to be writing AQ, which remember stands for aqueous, or in solution. Okay, so what happens to chlorine then? What does it become? Cl minus. Also aqueous because it's now in the solution. What happens to the water? Nothing. It stays as itself. So when we're writing the KSP, just like if you had a situation in math, let's say you have 4 plus x equals 2, let's not do that, 4 plus y. What can you do with the 4s? You can get rid of them because they're the same on both sides. You can do the same thing with chemical equations as well. So I wrote the H2O in here to show you that we're dissolving it in water, but because the water is the same on both sides of the equation, we don't ever have to write it again. All right, so now let's write our K, our equilibrium constant for this equation. Now it's called KSP because it's referring to this specific type of chemical equation. Okay, so the reason it's called solubility product is because there is no denominator in any of these KSPs. Why is there no denominator? You're starting with a solid, and solids are never included in the K. And so therefore, the result of a multiplication is called a product, just like the result of a dividing is called a quotient. Multiplying things together is called a product, so that's where we get the name solubility product. You're talking about the solubility of a compound, whether it dissolves in water or not, and because the math that results is from a product or multiplication, that's where KSP comes from. There really isn't anything very difficult about this, but like I said, the attention to detail must be there. Otherwise, the number of points that you will lose is just outrageous. So bear with me. We're going to go through many examples of this, but I need you to be looking carefully at your pink sheets and at your periodic table to make sure that you know what charges ions have, because that'll really be important. All right, so let's take a look at some examples. Usually what you'll get in a problem like this is the name of a compound, and then you'll have to write the equation for its solubility and its KSP. So let's start with this one as an example. Okay, so your chemical equation always starts with the substance that you're given as your one and only reactant. And what it breaks down into are its component ions. So now here you have to know a little bit about chemistry. So how will this break apart? Well, there are calcium and there are chloride ions. What is the charge of calcium? And its state of matter must be AQ. So you have to write those little letters after each of your ions. Or after all of your species, really, because it should say solid as for your reactant. Okay, so now what's the other ion? What's the charge of chlorine? Notice how I did not put the 2 down here? It's because it doesn't go there. Chlorine does not exist as Cl2 minus. How do I know that? Because this is where I have to know the chemistry. How did I get this compound's formula? Well, originally, from olden days when we learned about how to write compound formulas, we start with their charges and then we think, are these 2 numbers the same number? No, they're not. And so we have to move this number here and this number here. And that's how I knew to write down CaCl2. So that 2 is not here because this is its chemical identity. It's not. It's just showing you that there needs to be 2 chlorines to balance out the 2 positive of the calcium. So that 2 has to go someplace though. So we put it in front to show that there were 2 Cl- ions that participated in making this compound. Okay, so then your KSP for this equation. Now I do need you to write aqueous in both of these product species, but I don't need you to write it when you're putting it in KSP. So it's okay if you do this without putting the aqueous there. But then don't forget your 2 as your exponent for chlorine, because the exponent is always the stoichiometric coefficient. Does this make sense? All right, let's make it more complicated. Next example, let's do this one. Now, if you have more than 3 capital letters in any compound formula, it means that you have something from your hot pink sheet. It means that you have a polyatomic ion, always and forever, amen. So that means that if you don't have all of the charges and what they look like memorized, be good friends with your pink sheet. Okay, so this is my one and only reactant. Sodium, we already talked about, is a +1 charge. Of course, we don't write the 1, so don't be doing it. I'll be marking it wrong now. Just write a plus or a minus, no 1s. And then NO3 appears on your pink sheet just like this. So why did I not do this? That's a terrible looking thing. Why did I not do this? Hunter?
You don't need 3 ends.
I don't need 3 N's, but I still need the 3 O's. Yes, Mason?
So it exists peacefully as NO3.
It does exist peacefully as NO3. Yes, you're right. So this is sad face, this is happy face. So those little numbers you have to be careful about. You have to understand your chemistry. And you do, you just need a refresher on your pink sheet probably. All right, let's do another one. Let's do... I have a better idea. I'm going to write a name on the board. And I want you to write its formula. So if you see something like this on your homework, yes, you could absolutely say to your phone, hey Google, or hey Siri, what's the formula for aluminum hydroxide? And it'll tell you. And that's nice. But if you don't know how to do it on your homework, you're not going to be able to know how to do it on an exam. And I can promise you that if I'm asking you how to do this on a homework, I'm going to ask you how to do it on a test. Okay, so how do we do this? Well, all you have to do is figure out where aluminum is on your periodic table and find its charge. It is
3+.
And then what's hydroxide? Where would you find that?
Pink sheet.
Pink sheet? It's OH minus. Are these two numbers the same?
No.
So then they have to get switched. And so your compound's formula should be with parentheses. If you're modifying any polyatomic ion, that's the one and only time that you use the parentheses. Don't use them if you don't need them, but you must have them if you do need them. Okay, so then remember we need a little s there.
Mr. Bishop?
Yeah.
So if it's on a pink sheet, you need parentheses?
If you're modifying it.
Okay.
So, for example, like when we had Na and NO3, I didn't use it because I didn't need to, so I could just write it like this.
All right, yeah.
So only use it if you need to, but if it's on the pink sheet and you're modifying, you do need it.
Okay.
Good question. Okay, so we already figured out what the charge of aluminum was. So we can just write that in as our first product. And then what should be my product for the OH? Mason?
3 OH minus.
Correct. So because we said that we needed to have 3 of this substance to make our balanced chemical formula, we need to have the 3 here. A good handy trick is if it exists on the periodic table with the little number or on your pink sheet with the little number, you should leave it at the end. If there is no little number 3 at the end of OH for hydroxide, it must come in front. Okay, so this is only half of your work, though. You need to do the KSP as well. And the KSP for this equation would be aluminum 3 plus times OH minus to the 3rd power. How's that? Okay, good. This is the hardest kind of thing you'll see. This is hard only because it's hard for us to remember how to name these kind of compounds. Iron 3 does not mean this. Iron 3 means this. That number in the number in Roman numerals tells you the charge of that ion, not how many of it there are. Okay, NO3 is nitrate, and it has a charge of -1. So my proper compound then, these numbers are not the same, so I'm going to have to move them. And so my proper compound for formula for iron 3 nitrate should look like this. Is that coming back to us a bit? So then to finish this off, we know the charge of Fe. We know the charge of NO3. What should I do with this 3? Put it in the front. And so then my KSP will look like this. "18 minutes. I have a homework for you that is 100% of just doing this. This skill is not really anything new. We've already learned how to do all these things, but it's so important that you can competently go from this word, from this wording to this chemistry. It's so important that you do that I'm giving you an entire homework of just practice for this. Now, this homework is due on Friday, but it is just a one-sheeter. And you have the whole rest of class to work on it. Now, we are also, give that to me. We are also going to do a lab on Wednesday, so I'll give you the lab papers for that as well. You have the entire time, the rest of time, as time as your own to work on this and the lab.